So before we start this next page, I wanted to remind you of a previous section on the first derivative test. What was the whole point of the first derivative test? Well, the first derivative test was used to find relative or local extrema. It tells us when do we have a maximum and when do we have a minimum. So what you do is you look at the sign chart for the first derivative. If the first derivative went from positive to negative at a critical value, then we knew that that point right there was a relative or a local maximum because it went from increasing to decreasing. We had if our second derivative went from negative to positive, my original function went from decreasing to increasing, which made that point right there a local minimum. Again, what did the test do? What is the point of the first derivative test? So the first derivative test, the whole point of it is to give us relative extrema. It tells us we have a maximum anytime our derivative goes from positive to negative, and we have a minimum anytime our first derivative goes from negative to positive. So, what are we learning now is called the second derivative test. What's the point of the second derivative test? It's the exact same thing. The second derivative test tells us the exact same thing, relative extrema or local extrema. The point of the first and the second derivative test is the same thing. How do you find a maximum or a minimum? The title tells us what we're going to use. The first derivative test tells you to use the first derivative to find relative extrema. The second derivative test tells us to use the second derivative to find relative extrema. So how does the second derivative test work? Here's the idea. If we have a critical value, a point where the first derivative is equal to 0 or undefined. Again, we want to find the critical values where the first derivative is equal to 0 or undefined. What can we do with that point? Well, one way is to do the sign chart on the first derivative. But what's really nice is sometimes you don't even need to do the sign chart. We could use the second derivative. If the second derivative is easy to find, we might prefer to use the second derivative test. The second derivative test says, look, if you have a critical value, and at that critical value, it's concave up, that point right there, concave up, means my second derivative must be positive. So if it's a critical value where the second derivative is positive, that point is a relative or a local minimum. If you have a function where the second derivative is negative or it's concave down at that critical value, then that second derivative is a relative maximum. So that is our second derivative test. Find the critical values where the first derivative is equal to 0 or undefined. Then, rather than doing a sign chart, find the second derivative. Take the critical values and plug them into the second derivative. If the second derivative is positive, it's concave up, which makes that point a minimum. If we plug it in, that critical value into the second derivative, and it's negative, it's concave down, which means we have a relative maximum. We don't need to do the sign chart at all. So let's look at example 5 here to help us figure out how to use the second derivative test. Again, the second derivative test tells us relative extrema, the exact same as the first derivative test. The advantage is we do not have to use the sign chart. So look at this example right here. Our function is x to the fourth minus 4x cubed plus 1, and we want to find the relative extrema. The first derivative, as this is a polynomial function, is pretty easy to find. It's 4x cubed minus 12x squared. We want to find the critical values, so we want to set that equal to 0. Notice this is never undefined. Because it's a polynomial function, it is equal to 0. I can factor out a 4x squared from both of these terms. If I factor out a 4x squared, I'd be left with an x minus 3. Set each one of those terms equal to 0. I'd end up with x squared equals 0, or just x equals 0, dividing both sides by 4, then taking the square root. I have x minus 3 equals 0, which is going to give me x equals 3. So these two numbers right here, because they're in the domain of the original function, these are my critical values. So if I was doing the first derivative test, this is where I create a sign chart, pick numbers, and plug them in. I'm telling you with the second derivative test, that is not what you do. With the second derivative test, now we want to find the second derivative. The second derivative of this function is quite easy to find as it is a polynomial function. So for the second derivative, I would have 12x squared minus 24x. Again, we don't need to set this equal to 0 or anything like that. We're not finding inflection points. All we need to do is plug those critical values that we found from the first step, which was 0 and 3. We're going to plug those in to the second derivative to see if it's positive or negative. So let's do that now. We have two different x values that we care about, 0 and 3, and we're plugging those into the second derivative. The second derivative of the function being 12x squared minus 24x. If it's positive or negative, that tells us whether it's concave up, which would make a minimum, concave down, which would make a maximum. Let's see what happens. When I plug in 0, it looks like I'd actually get 0, which is neither positive nor negative, which means the second derivative test fails. It doesn't tell me if it's concave up, concave down, so it doesn't tell me whether it's a max or a minimum. When I plug in 3, it would be 3 squared, which is 9, times 12, minus 24 times 3, which is a positive number. Because it's positive, I know that this graph is concave up. Because it's concave up, think about that point right there. I know that point is a minimum. So from the second derivative test, we don't know about x equals 0. We'd have to go back to the first derivative test on that one or look at the graph of the function. But we do know when x equals 3, we do have a minimum. Again, a minimum is a point on a graph, so we do want the ordered pair, meaning we do need to plug 3 into the original function, so let's do that now. F of 3, plugging it into the original function would be 3 to the 4th minus 4 times 3 cubed plus 1. Use your calculator to get that, and I'm getting negative 26. So that tells me the point 3, negative 26, according to the second derivative test, is a minimum. 3, negative 26 is the minimum. Maximum is none. So, because it told us to use the second derivative test, we don't have to worry about x equals 0. If we wanted to, we could do the first derivative test at x equals 0 to see if that's a maximum or a minimum or neither as well.